I'm Venkat Guruswami. I'm the director of the Simons Institute for the Theory of Computing, and I'm here this morning on Friday, March 13th, with Professors Dan Spielman and Nikhil Srivastava, who are two of the organizers of First Proof, an exciting initiative to measure the capabilities of AI models to do research level math. In round one, the team took 10 questions from their research to which they knew the answers and posed them with a week given to AI models to try their hand at these questions. And there was a lot of interest in the ensuing week, and the results produced were quite striking. Many of the models managed to produce highly plausible and often correct answers to these questions, which were really at the level of what we work on as practicing mathematicians and theoretical computer scientists on a day-to-day basis. But it also reveals certain bottlenecks in terms of verification of the solutions, which were sometimes not that easy to verify and took a long time, as well as issues on how do you judge how autonomous the solutions were produced. And it is these bottlenecks and challenges which has prompted the team to announce the launch of the second round of this exciting initiative tomorrow on Pi Day. So that's why I'm here with Dan and Nikhil today to talk about their experiences from the first round, as well as what we might look forward to in the second round. So thanks again, Dan and Nikhil, for making time to chat with me this morning. And let's get started by discussing why you're doing this project.
People are already privately experimenting with AI in their own research. But there's a value to doing this in public, because otherwise there's this kind of selection bias that you only see the positive results, and often those results are like concentrated in some area of math, and you don't really get a picture of how this distributes across different areas of math, different levels of difficulty. And so in curating these problems to cover a broad range of areas and to be at a kind of particular part of the mathematical research process, we're hoping to just bring clarity for the mathematical computing in general about these capabilities.
So I'm very interested to know how LLMs can help me in my research. And I think, all of us are. We are all hoping that large language models will help speed up our workflow. I mean, we also hope they don't make us irrelevant, but that's not something we're able to address through this challenge. So I'm hoping that through this process, we will gain some understanding of what are reasonable expectations to have for what we can do with the large language models. Because if you try to ask them to do too much, you spend a lot of time waiting through output that's not actually very useful. So we want to get a good mental calibration for how they should help us. And what I am most interested in is actually what I can do with the large language models that are available to me. In contrast, a lot of AI companies are writing papers or press releases about what they've been able to do with their own internal models. And that actually is not particularly valuable to me if I can't use those models or see those models or even see them in action. The way I describe this to someone is as if a shoe company told me that they've got a new shoe in which everyone who wears it can run a 4-minute mile. But you can't buy the shoe, you can't see the shoe, and they won't even disclose the videos of their own staff running 4-minute miles wearing the shoe. It's not actually valuable to me, even if I believe it's true. Now, I place a little more faith in my colleagues at some of these companies than I do in, a random shoe company. But still, it's not actually useful for me to see these press releases. I want to know, what can we do? And that is part of what we were getting at here with First Proof. When we set out these problems, we did check our questions or lemmas against the current large language models that we could access. And we released the questions also to the public, and that's how we got responses from different companies and other groups trying to use large language models to solve our problems.
Great. Can you reflect a bit on how these motivations set the criteria you set for these problems, which you chose in First Proof?
Yeah, I mean, so the defining feature of the problems is that they arose naturally in our research. And so they're part of the process of proving new theorems. And there was a range of difficulty. Some took hours, some took weeks, and we didn't try to make them adversarial in that sense. And so there was some kind of a sample from the distribution of day-to-day mathematics and theoretical computer science research. And that's what made this different from other benchmarks where the problems were kind of engineered with different criteria in mind, such as being easily gradable. And indeed, our problems were not easily gradable. Like the answers were proofs, and that was something that came up a lot in the first batch.
Yeah, one thing I think that was really critical are these questions we asked are the sort of things that we are spending our time on. So they're the sort of things where if a large language model can speed up a lot, that can help me and save me time. Probably. I mean, there's also a risk because when I'm working on solving things, I learn things in that process. And I learn more about what my techniques can do and what they can. And if someone just gives me the solution, I may actually learn less. So, there's a bit of a mix. But still, these are the sort of things we do think that, yes, if I spend 5 days on this and a large language model can give me an answer in one, that will probably help me out.
So, given that, what are some interesting things you learned from this experiment and which happened in the first round?
I mean, the first thing we learned, which we didn't know before we did it, is that people are interested in this kind of activity. Like the math community was generally supportive of it, and the AI companies were also interested. AI researchers were also interested. We weren't sure of that before we did it, and that was one of the reasons to do it before going for a more formal benchmark, as we will in the future. The other surprise was that, in our internal tests, like public models could solve two of the problems. Essentially, their solutions were fairly close to things that were already in the literature. And I was surprised that in this, informal first round, solutions to many other problems were produced. And that's, that really caught my attention, and I think caught the attention of a lot of people.
Right. To build on that, AI companies, use their internal models to work on our problems and provided provided solutions to many of them. And well, as Nikhil said, both we were sort of happy to see that they were interested in taking up our challenge and interested to see what they could do with their own internal efforts. We do really want access to that because, they solved many more problems with their internal efforts than we could do with the publicly available models. And there have been some improvements. Things are changing very quickly. So one of the problems that LLMs used to have is they would be very confident. They'd tell you, oh, yes, here's the solution to your problem. Some of them are getting past that. Even when it's totally wrong, they would say, here's the solution to your problem. That really is not helpful when, they assert to have solved something and you spend 3 hours trying to figure out why it's wrong. Some of the large language models are now much more comfortable with saying, I don't know how to solve that. Here's what I can do. That's a big improvement to see. Overall, I think people discovered that there are many sorts of different voices that come out of large language models. And we saw a wide range of those. So one of the voices I described at first is the overconfident one. Or I don't know if it's overconfident, or sometimes I'll model it as like a deceptive student. Someone who's trying to hide the mistake that they made. Other voices, one solution we saw I describe as a student who an hour before the homework was due got the answer from someone else, didn't fully understand it, but wrote it down. So you get a solution that uses a lot of the right words, but it feels like the person who wrote it didn't understand it. I mean, again, that shouldn't be surprising. I don't know what it means for a large language model to understand something. Maybe it doesn't understand what it's writing. Probably, I don't even know what it means for it to understand it. But yeah, there was one solution sent to us by a company that has that flavor, which made it very hard to read because it's not the way someone who understands the material would write it.
So, yeah, and I mean, building on what Dan said, verification became a really major focus. Usually in research, we think that, okay, writing, generating the proofs is the much harder part, which maybe in some sense it is. And then verification, okay, as being a journal editor, is like a serious thing. But in this case, it was like kind of it was like a reverse, like P versus NP kind of thing, that the generation was easy and the verification required lots of human effort.
And was that because like details were skipped, or maybe the most crucial part where details are needed is skipped a little bit, like the student which Dan was referring to,
Mhm.
or were there confusing missteps? Like, is there any particular reason this was the case?
It was a bit of what Dan said, but it was also the highly specialized nature of the problems. Like
Mm.
this is different, very different from Olympiad problems where, an undergrad knows all the math that's needed. For these problems, you really needed to be an expert to even understand what the problem was. And so there were very few people who could do these expert reviews. And the mistakes were subtle because of some of the things Dan mentioned. But in the end, this informal kind of community conversation did lead to some level of verification of many of the solutions. And one surprising thing that happened that wasn't part of our original goals was the formalization community, which I guess you've also been thinking about, uh, joined in. And, as of now, I believe they've produced lean proofs for 3 of the solutions, which is kind of amazing. I mean, to me, I don't use lean, but it seems amazing.
I mean, I'll add another thing they did. There was someone who took the proofs that we had written and proofs that other teams had produced and fed them to a large language model, asking it to critique them and find mistakes. And yeah, some of the proofs made by AI companies got higher scores than our own proofs written by the experts. I mean, one of these looked at my proof of my problem and it pointed out, oh, one place I, wanted to use one lemma and I instead gave the number of a different lemma. And, one case I said, choose an arbitrary vertex. And I could only choose most vertices. Like there were simple errors, but it found them. Whereas like 3 people who I'd given my solution to didn't notice those errors. So that was pretty cool.
Hmm.
I'd say other things that made it hard. Well, yeah. So, like the solution, which I described as the student who copied their homework, spent a lot of time or space writing about easy things and gave much less effort to writing about the hard things. So, when you see that, you think, like, oh, they're bluffing. Um, Partially, I think our difficulty in reading these and grading them is just experience. With most of us have used large language models before and seen the sort of mistakes they make. And at least some of them, the mistakes are horrendous. Like, you've got 5 pages of proof, and the mistake is it said that zero's larger than one somewhere. And this is a mistake that one of your colleagues would never make. So if you see some sort of calculation done by one of your colleagues of that form, you don't doubt it. Here, suddenly you're wondering, like, where is it hiding the mistake? To some degree, our experience, at least my experience of the last year in using large language models, has bred a lot of distrust. Therefore, I spend a lot more care looking at what it says. Maybe, if there's a lean proof, then I'll have more trust.
Yeah.
I mean, it sounds like we're making it sound like it was a grind, but there were some really interesting things too. Like there were cases where, these where new proofs were found, which is
Yeah,
like really exciting.
it
Yeah,
is.
I
Yeah.
heard that in fact for your own problems, the solution found was different from what you had in mind. Was that true?
Yeah, for my problem, yeah, 2 companies that produce solutions, both were different than the ones I had in mind. I mean, it's not shocking because it wasn't a crazy statement. I mean, I know better proofs than the proof I wrote up. The proof I wrote up was partially chosen for its readability rather than like for making anything tight. I wanted it to be readable and verifiable easily. And where it wasn't, I think Nikhil scolded me. So yeah, I made it a little better. But yeah, it is really cool that different proofs came out.
I mean, I
So
think for my problem, it was a different proof than I didn't know that proof, and that was quite amazing. And the thing I was really curious about, I mean, which made me like really excited. I was like, well, how was this produced? And this is where, we hope in the second round we'll have more clarity. Like we will have the solution concept will be that there's a proof, you check its mathematical correctness. We also have some kind of transparent view of how it was produced, which would then allow you to interpret, a lot more clearly what it means.
Yeah. So
Great.
one
Yeah,
of the things
go
sorry,
ahead,
so
Dan. So, yeah.
things I'm hoping to get out of this process, and one of the reasons it's really helpful to have the AI companies involved, even if we're only using publicly available models, is I want to know how to use their models as well as possible. And they know that. At least they have some idea of that. So I hope we get guidance from them on how best to put these queries in their model, or really, what are the right prompts to use? Because then everyone benefits when that becomes public and everyone understands that.
Or some kind of like harnessing mechanism or something. Yeah.
Yes. Yeah.
So, yeah, given this backdrop, what is the second round, which you're going to launch tomorrow, I believe, about, and how will it differ from the first?
Well, okay, so we're going to announce the details of the second round tomorrow.
Sorry, yeah.
Actual, round will occur in May or June. So the main difference is that in addition to this informal community experimentation kind of thing that we already saw, we're going to have a formal benchmark component. And in that activity, the main differences are there's going to be a formal grading process, as in we're going to grade the AI generated solutions as if they were submitted to a journal with like multiple reviewers and, double blind reviewing and things like that. And we're going to insist on being able to verify that the solutions were produced autonomously. So for this formal benchmark, where we played with various ideas on how to do that, and the only one we were able to find for now is we simply run the test ourselves using API access to some public model. Now, if we get enough funding and things like that, we may be able to upgrade this to we can run, a harness on top of a model in some sort of trusted environment. But that would give a very modular what's inside the publicly available model. That would give a clear view of how, like a very precise view of how these solutions are produced. And so we hope that this will have a clearer scientific interpretation, this formal benchmarking round. That's the main difference. And yeah, we hope to cover areas of math that were missed in the previous round and things like that.
Yeah. I mean, we've had a lot of discussion over how to organize this. And there are drawbacks to our approach. Like, for example, we know that usually if you're using an LLM to try to solve a problem, you're going to interact with it a lot. But we don't know how to do that in a way that doesn't contaminate the process with the expertise of the person interacting with the LLM.
And I was going to ask whether it is okay, would just giving you the entire transcript, including the prompts, wouldn't address that issue adequately.
Okay, so I know that when I'm using large language models, I interact. Okay, it's not always a fruitful interaction. Sometimes it gives me a proof and then I point out the mistake and then it says, oh, I'm sorry, that was a mistake. But yeah, really, the more interaction you do, the more the results are about the person who's doing the interacting and less about the large language model. Like, I'll give an example. So one of my graduate students, Shifan Yu, recently proved a conjecture of mine from a while ago about finite free convolutions. And he spent a lot of time with a large language model working on this. The large language model gave him, okay, first of all, he spent a lot of time before the large language model. So he did a lot of work. The large language model gave him a lot of things that were not correct. But he really persevered and spent a lot of time with it, asking it a lot of questions. And finally, it led him to some things that have helped him to the proof. And I think actually for a lot of people, reading that transcript would be interesting, but it should not be taken as a proof that was written by a large language model. It was a proof that was written by Shifan with some assistance from the large language model, but it's really about him realizing what's important here, him setting up the problem correctly, him figuring out which avenues to pursue. So then less credit goes to the large language model. If we want to figure out what large language models can do, we don't want to have really what they can do with a really talented human talking to them necessarily. Or maybe we'd like to know that, but we don't, it doesn't feel as replicable or as useful knowledge.
I mean, another way to put it is we're kind of setting up this experiment to see what is the like, you know, what is the largest unit of work that these models can do by themselves. And that's supposed that we hope some kind of proxy for their usefulness in the interactive context. And that's also how we've, chosen the problems, right? We haven't, I mean, actual math research involves a bunch of other things like asking questions and maybe even making definitions and approach frameworks and then solving specific problems. And so a kind of guiding philosophy is to identify the largest unit of mathematical work that can be done autonomously.
What do you hope these projects will achieve in the long run?
I mean, scientifically, I hope well, we'll continue to get clarity about what the capabilities are as they advance, and they're moving very fast. And so we hope to repeat this every few months, and we think this is useful information for the research community to have. But there's also kind of a sociological goal, which is we think these type of activities are a good place for interaction between mathematicians, DCS people, AI researchers, people working on formalization, AI companies. Like one of the nice things that happened in the first round is there was after this informal experimentation, there was a Zulip chat, and things that we didn't predict at the beginning kind of happened. That we posed these problems, and some various people produced solutions, and then some other people who were more interested in formalization came along and figured out a way to formalize the solutions, also with the help of AI. And then there was a nuanced discussion about, well, how should the grading be done? How can we leverage AI to do grading? And I think it's beneficial for these kinds of conversations to happen in public, and this activity supports that.
It will help everyone learn how to use these tools, which I think is really important. I think I used to identify what were really important skills for graduate students in theoretical computer science to learn. Chernoff bounds, probability. We can go into like certain areas of mathematics, but they have
singular value decomposition.
Yeah. Yes, they have to learn how to function as a scientist. They have to learn how to give talks. Learning how to use large language models is going to be part of that. And learning how to use these new AI tools to do their work better is going to be part of that. And why do they have to learn it? Because if they don't, they won't be the best. The people who do know these things will get the most done. So we want students to learn this, and yeah, probably even more so, we want us older folks to be able to learn how to do this. One thing I'll say that's always been amazing to me about the theoretical computer science community is that a lot of the best work is done by graduate students. And it's sort of amazing because when I talk to people in other fields, this is not always their experience. But, I try to explain why this is, and I think it's because the graduate students can learn all of the newest things and they have time to synthesize that information and put it to use and make new discoveries. And, when you're older and you have more responsibilities, you don't always have time to do that. So I think one of the things we want to do is spread this knowledge as far as possible so that young people can learn these new skills and so that old people can also keep up.
That's fascinating. But I want to circle back before we close to one of the points Dan made at the beginning, which is about these models being internal and us on the outside not having access to them. From what I understand, not just about the models, but the amount of compute which gets thrown at in trying to solve these challenge problems. So do you see an issue in making, whether we will on the outside or the general mathematical public will have access to models which can use that much compute, or would that ever be viable to throw that much compute for mathematics done at scale by thousands of people? And what that might mean for the practice of math research? Of course, and this is a little bit speculative because we don't know how these things are going to shake up in the next year, but I would love to hear your take on this.
Yeah, I mean, so let's see. So what do we know about what happened in round one? So one team reported that for one of the problems, they used an order of magnitude more compute than they did for, the the hardest problem that they solved. So we do know that somehow a lot more compute um, is used. And this, I mean, in round two, where we're going to strongly suggest that all solutions come with an estimate of the amount of compute, so we can have a conversation about this, because it really leads to like different futures for research math. Like one possibility is that, yeah, it takes a lot of compute now, but it'll all become cheap and everybody will have access. Another possibility is it becomes a very resource intensive activity and you need a lot of compute to do research.
Mhm.
I don't know, Dan, do you have any?
Yeah, I mean, I worry not just about the compute, but about the money. Right. It's completely possible that there's a future in which to do good math research, you need thousands of dollars per month or per week in access to, just like the same way like chemists or physicists need materials. It might be that we need money to make LLM queries in the future to do good research. Or maybe, as Nikhil was saying, we won't. One of my colleagues, Johan Ugander, suggested to me that this techniques behind large language models might become sufficiently commoditized that you can essentially run your own on your own compute server, maybe 3 years from now, and that'll be good enough. We don't know where this is going to go. We'd like to find out and at least be ready for either outcome.
So, on that vein, Dan, are you at all, and Nikhil too, are you at all concerned about potential detrimental effects of all these developments to the practice of math research or math research as a profession?
I'm very worried about our ability to train graduate students because the way we often train graduate students is we give them problems to work on that hopefully they can solve. And then when they do that, they gain some self-confidence and they also just sort of learn what the process of solving problems feels like. And then they go on and can solve harder things. And the worry is if they can do that initial work using a large language model, one, it might be discouraging. Two, maybe they never actually learn what it feels like to solve those problems and never go on to then solve harder things. I look, let's put it this way. It's a worry because it means I know we're going to have to change how we train graduate students. What I don't know is will we come up with a way of doing it that successfully produces graduate students who can thrive in this new world?
Yeah, that's a valid point. We're already facing that at level of education where we are not able to give homework problems. So increasingly we have to, evaluate people based on tests. Now that's not really viable or even appropriate to do for graduate students and research. So it's definitely something to think about. Yeah.
That's
I
right. But
mean,
you're
it could,
right. Oh,
go ahead.
sorry, Nikki.
I think it could become a little bit closer to undergraduate education, and you separate the learning process from the producing new results process. That, even if certain level of math is doable by AI, it might still be worth it for humans to do it just to learn.
Mm.
It is. But I worry a lot at the undergraduate level because the things that I want my undergraduates to learn that could one day turn them into successful graduate students or more of a successful people can't necessarily be measured in a short test. And it's getting harder and harder to assign them things or homework or challenges for themselves that large language models can't do. Now, it might be that those students who are really motivated will accept our challenges anyway and do them. But we still won't be able to distinguish the students who did that from the students who didn't, unless, it's through conversations or something like that. And, if you're at a small liberal arts college, you have the luxury of being able to talk to your students and know them. If you're at a really big school, that's almost impossible. So we're going to have a harder time not just training the undergrads, but also advising them and figuring out which one should go where.
I mean, I
Great.
think
Yeah.
for all these things, like that's part of the reason to have like public conversations about this early on as things are changing, because the change is going to happen, and I mean, we have to embrace the change. We can't deny it.
Yeah. So to close, like what broader takeaways would you like to leave for the listener? It's really all fascinating. Things are changing very rapidly, as you said. So any final words of wisdom and what we should
So,
expect in the coming rounds?
okay, so so I'll just think about what we should expect from the large language models, and Nikhil, maybe you can talk about coming rounds. I mean, for me, I'm really curious to see where this goes. Do large language models keep improving as much as we've seen them improve in the past year? Should it be a similar improvement the next year? Not that I know how to quantify it. Now, I know people are very attached to these scaling phenomena, that they've observed that things keep getting better and better and keep scaling. But I don't know that will always hold. Like when I look at my children, boy, they learned an amazing amount between 0 and 5 and 5 and 10. And I'll say, like, I even learned an amazing amount between 20 and 25. But if I try to extrapolate from my experience of age 20 to 25 to like mid 50s, I'm really disappointed. I did not learn nearly as much in the last 5 years as I did in those 5 years between 20 and 25. Are large language models going to hit the same obstacle? I don't know. This is one of the things I really want to see. I think if we keep running multiple rounds of first proof over the next few years, we will see that either this is taken off an amazing degree or maybe it'll hit a plateau.
Yeah, and we do plan to kind of adjust as needed, right? Like if these things get saturated, then as I said, there are many other aspects to math research. Like you can make the problems harder, but you could also ask, well, can it ask interesting questions, or can it make definitions? Like all those things are on the path to seeing whether it can really match or exceed the abilities of humans. Yeah.
Yeah, that's fascinating. I greatly look forward to what you have on tap for the second round and more. And thanks again, Dan and Nikhil, for the wonderful conversation. And all the best to you on the next round. And look forward to the problems and the results, both human and AI generated. So, thank you very much.
Great. Thanks, Venkat.
Yeah.